Thank you very much. I'm very glad to be here. So I'll talk about abstractions for multi-material 3D printing. You probably have seen that multi-material, that 3D printing is really everywhere you pretty much see. And for example, lots of different magazines, books, lots of stories in the media. But it's really interesting to look what 3D printing is used for these days. Business analysts, of course, have a very look at this market and come up with many different categories. But if you look closer, you can group this in roughly 3 different parts. One part, the blue part, is what we traditionally think as the 3D printing, which is basically prototyping used for presentations, for research, for education. But there are these 2 very big components that are rapidly growing. One of them is the use for manufacturing. So, for example, for using molds, casts, or tooling parts for manufacturing. And then there is this green part. This is fabrication of real functional parts that actually are used as products. So this green part over there, that's roughly a quarter, hasn't been there roughly 10 years ago. So it's very, very interesting. And this is, on the top of that this is really growing at a very, very large rate. I would like to give you a few examples of current uses of 3D printing. So, for example, Aston Martin has been looking into rapid prototyping of models of their vehicles, and they build it from composing different parts built using 3D printers. And these models have been used, for example, in the movies, for example, in the latest James Bond movies. GE Aviation is really interested in 3D printing, especially metal printing. So to give you an example, this is a fuel injection nozzle that traditionally has been built using 18 different parts, and now we can 3D print this part directly as one part, and it's much more durable and much lighter. And this is not just building a single component. GE is planning to build thousands or tens of thousands of these components. Nike is also pushing the boundaries of 3D printing. For example, this is a real product. They are marketing these football cleats with specially printed plates, and the special structure of this cleat can be only 3D printed, and it gives you supposedly very, very high performance. Hobbyists, makers, and prosumers, they are really embracing this whole trend. So, for example, they are using it to scan, 3D print different figurines, but they're also trying to build real functional parts. For example, this is a real tape measure that has been produced using low-cost machines. And this is similarly 3D calipers, again printed using FDM 3D printers. My group at MIT is pushing the boundaries of 3D printing, and the trend that we are, and the subjects that we typically look at is multi-material 3D printing. Multi-material 3D printing is nothing more than 3D printing, but printing with not just one material, but with many materials. So I would like to show you an example. So for example, if I would like to print this piano, I'm going to discretize it into small volume elements. And then for each of these volume elements, I have a choice. I can pick not just one material, but from a palette of different materials. There are a number of different multi-material 3D printers on the market these days. Both 3D Systems and Stratasys have serious lines of these printers. Just to summarize the current state of the art, this hardware is extremely expensive. The underlying materials that people use are also extremely expensive. The material library is relatively small. These printers can use 2 to 3 materials simultaneously, so not more than 2 and 3. The software is in a pretty miserable state. Very, very limited software tools. There are really no material design tools, and everything as a system is very, very hard to use. So I would like to tell you about our approach to solving some of these problems. So let me first talk about the hardware. So our inside that we use, we do build 3D printers, but we use computer vision to assist building the hardware. So using this, we can build hardware that's very high resolution, 30 microns or better, relatively low cost because we can use relatively simple components, off-the-shelf components, and use computation to fix some of the problems. We can print with multiple materials, up to 10 materials. The whole structure, the whole system is extensible. And we can bring in additional we can both bring new parts, and we can also add components to the printer, and we can also integrate prints with auxiliary components. So this is a hardware prototype roughly from 1.5 years ago. Standard positioning system in XYZ coupled with inkjet printing and very modular trays where you can actually attach different subcomponents together. This is a smaller, refined version of this prototype from last year, and we are working on a completely new version this time. I would like to show you some of the subcomponents, for example, computer vision. Using computer vision, you can calibrate the system extremely well. The way you do it, you first put a calibration pattern on the tray. The system automatically scans this, and it can compute the calibration of the platform with respect to the positioning system. You can also print with the nozzles of the printer, and you can calibrate the positions of the droplets of these nozzles. And this can be either using a user-assisted way or completely automatically. So basically, you get a complete correspondence between where you inject and where the system is actually firing the nozzles. Yes?
Do you do your calibration prior to making a parts run, or do you do it concurrently with making the part?
So this is a very simple. Step, so it can be done at pretty much any time. We typically do it first, but I would like to talk also about the closed feedback loop. So this is another very interesting feature here. We can actually use a system. Let me go back. We actually have a very high precision scanning system that allows us to estimate the depth of all the parts at a micron resolution. So this is used as a closed feedback loop for the whole system. So what does this give us? Well, you can actually do much better printing with this. So basically, if you would like, let's say you would like to print something that's very, very flat, right? You are going to print a number of layers. You are going to scan the surface, and then basically, if there are any imprecisions here, this is the surface depth map of something that's supposed to be flat before applying the corrective layers. And if there are any imprecisions, you are going to apply additional corrective layers, and then you are going to get a depth map that's within the resolution of the printer. So using this system, you can actually obtain much higher precision using this corrective printing. This 3D scanning system also allows you to 3D scan auxiliary components in situ. So what it allows you to do is to combine 3D prints with auxiliary parts. You can simply place a 3D part over there, and you can actually print either on the top of that part with accurately aligned 3D model. So this is an example of hybrid printing. So what can we do with this type of system? Well, for example, we can print different optical components. We can print microlens arrays for example, with specially applied baffle. We can even print on the top of the surfaces or screens directly with correct alignment. We can print different metamaterial structures, for example, combining different elastic and rigid materials, and for example, in this case, building a material that has negative Poisson ratio. Basically, if you are trying to stretch it, the material is going to expand. We can print textured objects, different types of fabric structures with different, again, with combining different materials and maybe with different colors. Functionally graded materials, for example, a material where you change elasticity from something that's very rigid to something that's very elastic. So in general, we have a way of expanding the range of 3D printing by combining all of these technologies. I would like to focus more on software in this talk. So let's look at that. So if you look at current industry use of multi-material 3D printers, you will see that we currently print although there are capabilities of 3D printing with multiple materials, users typically pick one material per given part. So the main question is here, so why? Why one material per part? And I think probably the most important constraint comes from the designers themselves. Designers still think in terms of designing parts, in terms of designing using cut systems and only specifying one material per part. So we really have to overcome this sort of thinking, this limitation that we can design with only a single material per part. And there are, of course, more concrete problems. Well, there's a real lack of design tools. There are really no good design tools for these tasks. And as you will see, there's really a lack of scalable architecture that would handle the data size that multi-material 3D printing provides. So our group have been working on two different ways of improving software for multi-material 3D printing, and I think it's really good to look at both of them. So the first of these methods is direct specification. What do I mean by direct specification? Let's say I would like to 3D print a piano. If I would like to directly specify it, I'm just going to say that the top of the piano is made from this particular type of wood. The strings are made from this type of copper. The keys are made from this type of plastic. So that's direct specification. Functional specification works slightly different. I'm going to specify the piano in terms of its function. For example, I'm going to say that when the top of the piano is glossy with that particular gloss level, and if I hit the given key on the piano with the given force, I'm going to get a particular sound from the whole structure. So that's functional specification. Let's talk about direct specifications and challenges. Okay, so whenever you want to 3D print structures like this, you immediately realize that you have really problem with data. If you are printing at 600 dots per inch, then you have gigavoxel per inch cubed, or teravoxel of data per foot cubed. Well, and so that's the first one. And then there are lots of interesting ones. For example, you have building continuous gradation between materials at a very fine scale. It's extremely challenging. And it's very difficult to decouple materials from underlying geometry. And finally, you have real problems with being independent of the particle printer and its native resolution. So what we have developed is Openfab. Openfab is programmable and scalable fabrication pipeline. Openfab is inspired by rendering pipelines, and similar to these pipelines, for example, as Renderman or GPU pipelines, it has fixed stages and programmable stages. It allows you to do procedural surface definitions and material compositions within the object. It provides you with resolution independence, and it also handles the data sizes using a streaming architecture. So let's first talk about the programming model for this architecture. So similar to the rendering pipelines, it has both it has the following stages. So of course you specify the input. You have a number of fixed function stages. You have two programmable stages. These programmable stages can access different resources. And finally, you also generate the output in the form of multi-material 3D print. How does this work? Let me show you this on a very simple example. Let's build this teddy bear. So the input are going to be boundary representation, the shape. We're also going to specify phablets. Phablets are subroutines, little programs that specify both the surface detail and material composition within the object. And of course, we specify external resources, for example, textures or materials. So the first step here is going to be tessellation. We are going to figure out we are going to tessellate this model to micropolygons that are at the resolution of the printer. And then we execute the first stage of this pipeline. In this case, we are going to execute the surface stage of the phablet. In this case, we are going to apply a Perlin noise to distort the surface geometry. This can potentially have can have many uses. For example, if you like to create a model with some specific, for example, friction coefficients, you could apply this kind of microstructures to do that. If you'd like to have some special appearance, you could do something like this as well. Next, we enter the voxelization stage. So this means that we are going to take this highly tessellated display surface and we are going to voxelize it. And then we enter the second stage of our phablet, and this is the volume stage. This is probably the most interesting part of the whole pipeline. So in this case, we are going to execute this surface stage of the phablet. For each voxel, the phablet takes X, Y, Z position of the voxel, and it returns the material composition of the given voxel. So as you can see, this is a continuous material composition. 3D printers cannot really put continuous material compositions at a given point. They can typically only do one material in a given small volume element. So that's why we also have a dithering stage that takes this continuous distribution and applies something like Floyd-Steinberg error diffusion to actually compute the discrete assignment. And finally, we have the output. I would like to talk about OpenFL. This is our DSL for specifying these phablets. As you can see, we have one phablet per object. It has 2 entry points, surface stage and volume stage. I would like to show it on a very, very simple example. Building layered composites is a very important feature here. So in this case, we can build a multi-material composite in a very simple way. The phablet in this case takes a voxel center, and it has access to things like distance function. This is a sign distance function to the surface. And using this simple if statement, you can just assign materials based on this distance function to the surface. We also built a corresponding architecture that's highly optimized and can execute the whole process. We had 3 guiding principles. Well, first, we would like to have very fast startup time. So this allows us to start the print immediately whenever we submit the job. We also have streaming architecture, so we are going to divide our model into slabs, and slabs are going to be memory limited. So they are going to hold a few slices, and then we are going to process these slices from the bottom upwards, and this naturally handles the fixed memory that we have in our system. So all of these things give you a very scalable architecture. This architecture roughly looks like this. The first part here allows you to pre-compute the different acceleration data structures such that things like sign distance functions can be computed very efficiently. And then we have this loop that performs everything for each slab. It finds the objects within a given slab, executes the whole pipeline, and emits and dithers the voxels that are sent directly to the 3D printer. I would like to show you what we can do with this type of pipeline. Let's have a look at some of the results. So first, it allows you to do material decoupling. What it means that I can specify one external surface, but a number of different phablets. And as you can see, I can change the way, in this case, these Rhino models look by assigning the material, by changing the material composition within the volume of each of the Rhinos. It also naturally allows you to decouple the geometry from the phablet. And in this case, I can, for example, specify this foam structure, and I can apply this to this teddy bear. And I can also keep it, reuse it for later. If I would like to print, let's say, a Stanford bunny, I can apply this phablet to the Stanford bunny. We can do procedural surfaces with the surface phablets. In this case, we specify as input only the slab of material And then the shape of these lenslet elements are completely determined by the displacements from the base surface. So you can pretty much specify the surface analytically, and then the printer automatically is going to compute the desired shape according to some analytical formula. You can, of course, do procedural volumes. In this case, you can create these marble-like structures with Perlin noise volumetric textures. This allows you to, of course, do something more interesting. You can, for example, use these procedural volumes to build very custom fiber optics. So in this case, we are going to have one sheet of the material that's sort of completely planar, and then by changing the refractive index within the volume, we can specify how this light is going to bend and how it's going to be re-emitted on the other side. What's really interesting about it is that it allows you to build something like displays with arbitrary shapes. And the way you do it, you take a standard 2D display, you build your custom volumetric display, and print this sort of custom volumetric fibers, and then you can connect the display on one side and have a very nice display with unusual shape. We can start building also other types of functional objects. So, for example, using the system, we can design we can design only external shell using CAD. We can import this, and the rest, all the internal structures are completely specified using our volumetric phablet representations. So, for example, the handles, the whole foam structures within the ping pong paddle, and then all of the little dimples on the surface. Of course, you can build more and more complex functional parts. In this case, this is a complete ski that has been 3D printing, not the bindings. And in this case, we can design a ski that has both pretty realistic appearance properties and mechanical properties. So these are the results. These are the types of results that Openfab can provide. I would like to move to functional specification next. So as you have, as I have described before, functional specification is where we specify function of the object, and then the system is supposed to figure out how to translate these functional specifications to actually something that you can 3D print. So we call this process of going from specification instructions to something that you can print directly, a spec to fab translation. So how would the spec to fab translation work in the case of our imaginary piano? So in this case, I can do the following things. I can start with some material assignment to the piano, to different parts of the piano. I can use some simulation where I can simulate how the structure is going to sound, and I can compare this to our functional goal. In this case, this of course doesn't work, so I have to pick another set of materials, simulate it again, and compare this to the goal. If you apply this to 3D printing, especially multi-material 3D printing, this really doesn't work. Basically, if you just are going to try, it's really not possible to try all possible combinations over there. So this really doesn't work. So this naive spec to fab translation process has to be changed in some ways, and we changed it in the following ways. So instead of working in the space of original voxels and their material assignments, we are going to work in the space of reduced parameters. And we replace this random material assignments with some, of course, some optimization algorithms. So I would like to briefly tell you what these reduced parameters mean. So if you would like to design a given shape, right? So if you look at the set of shapes that are spanned by all possible voxel assignments, they are going to reside in some high-dimensional space. if you look at the space of pianos that can be described using, for example, multi-material 3D printing that satisfies our goals, this is going to be some set like this. The goal of our reducers is to be able to build these low-dimensional reduced spaces, design spaces, such that this design space is not going to be so much different between this high-dimensional design space for all possible piano designs. So we need tools for designing these reduced spaces. We have looked at many algorithms in computer graphics and in material science, in mechanical engineering, in robotics. And we sort of saw that these spec-to-fab translation processes share this type of structure. And when we look closer, each of these subcomponents have some number of different types of building blocks, and for simulation, for all these goal comparisons, optimization, people use pretty much very similar blocks. People don't really look that much at how to reduce the space of possible parameters, and what are the building components for those. Okay, so we have come up with a set of data structures that are used to solve these problems. So in particular, we have a reducer tree data structure that allows you to describe the set of that allows you to describe the space, your design space, and we also encapsulate the whole optimization and simulation process within a tuner network. So first, let's start with the reducer tree. Reducer tree is a fabrication-specific decomposition of the design space that's hierarchical. It provides us with the parameter reduction, and it subdivides the space in some non-overlapping subdivision. This reducer tree has basically internal nodes. Internal nodes provide spatial partition of the space, and the leaf nodes provide specific material assignments. When looking at the previous literature, we pretty much looked at, we found that it's possible to describe these reducer trees with a very small number of different nodes. So for example, one type of node that we typically see is a stratum node. This node takes arbitrary geometry and decomposes it into the outer shell and the inner core. We can subdivide this geometry using, for example, columns, using lower resolution voxel grids, using some planes, using some spline surface. The leaf nodes can provide material assignment, and one of these material assignments can be also a void material. They can be also parameterized material structures. So for example, if I have a foam-like material, I can change, I can have a low parameter model that describes this material. For example, the sizes of each of these holes can be determined using some parameter. So let me give you an example how reducer tree works for a very simple for an example of textured objects. So in this case, we are going to take an input geometry, and we are going to subdivide using the stratum node. Then we are going to take an outer shell, and we are going to subdivide using the column node. And then we are going to assign one material node to the internal surface of this node, of the stratum node, and this is going to be just one bulk material. And then finally, we are going to pick layered materials for each of the nodes in the columns. So this provides you in general with a fairly compact representation of the design space that has much fewer parameters compared to the original number of voxels. So what are the parameters that we have here? For example, stratum has the thickness, columns have width, height, and of course, the corresponding material nodes have as a variables the corresponding material IDs. And as you can see, of course, we can change all of those. Okay, so now we have our parameterization of the design space, and now we would like to actually optimize it, to tune it to given specific task. And for this, we are going to use tuners. Tuners provide an abstraction that encapsulate all of the simulation and optimization process within one building block, and they provide an abstract interface between essentially the tuner, between the nodes within the reducer tree and simulation optimization. So we can attach these tuners to any of the nodes in the tree, and then this node is the tuner node is responsible for tuning material parameters within a given within the material node. We can also attach the tuners to internal nodes with the tree. In this case, the tuner is responsible for optimizing the whole material assignment and the whole material parameters within the whole subtree. So how does this work? Basically, the tuner collects the tunable parameters, in this case, the width, height, and material IDs, updates the parameter values, and it can actually iterate within a given loop. We can optimize each node separately, so we can attach a different number of tuners to different nodes, and we can also specify the schedule for these tuners. We can also build the whole tuner networks that actually can share information between the tuners. So we allow communications between these tuners. I would like to show you what kind of things you can do within this network, within this system. So first, you can do things that are fairly straightforward. For example, we can build something that works fairly well for texture. So this is a fairly simple tree and a tuner network. In this case, the input is the geometry and the texture, and the output is a model that mimics this model and the texture. Once you design this, you can, of course, reuse all of this. So if you specify a different model with different texture, the whole thing is going to work again. We show that you can reuse a lot of these structures if you move to more complex properties. For example, in this case, if you like to build a functional specification and a specs to fab translation for subsurface scattering, you will reuse most of the corresponding tree. You will change the tuners, and you will be able to optimize this. Of course, you will be able to also apply it to different types of geometries as well. These structures also allow you to analyze different types of spec to fab translation processes. So in this case, we can actually compare different algorithms that people have proposed. So in this case, this is a structure. These are the so-called goal-based caustics. These are very complex lens structures that are 3D printed. And in this case, you have a light passing through the lens, and it can actually form a complex image. So one particular algorithm uses this type of tuner network and reducer tree, and we can compare this to another algorithm that sort of achieves very similar goal with different reducer tree and a tuner network. So it's very useful to compare between different types of algorithms. What is very nice about this type of structure is that it allows you to combine different processes together. So for example, if I would like to be able to optimize both deformation properties and texture, we can build a corresponding tuner and the corresponding reducer tree data structures. Okay, I would like to say how all these components fit together. So first you have hardware and materials, and the direct specification layer has to communicate directly with the underlying 3D printing hardware. And functional specification should really reside on the top of that. So the output of the functional specification should feed in as inputs to the direct specification. Is that all? Well, of course not. What's really important is being able to build applications and interactive design tools at the top of these abstraction models. I would like to show you a few examples of the things that we have done in that space. So here I'm showing a complete multi-material cut system where you import a 3D surface, a shell, and in this case we are going to build a wheel. This is a combination of tire and the wheel, and in this case I'm going to build a shader network style composition of different operators that are going to compose very complex structures. This is of course very much a speed up, but this we are showing on the top here as well the whole network of operators that are applied. This is very analogous to the shader trees that are used for rendering, where basically you have a small number of basic building blocks, basic components that can be combined in some creative ways and design some complex geometric structures. And of course, you have to provide things like different types of inspection tools. You have to be able to provide interactive preview tools and so on. So all of these things have to work at different levels of detail, because in the end, this model has potentially has a teravoxel of data. So you have to be able to evaluate these at interactive rates in order to provide interactive preview for the users. The second project that I would like to show in this space is computational design of mechanical characters. So people have been building these types of mechanical characters and robots for a while. The problem with this is that, of course, it is very, very hard. It's really restricted to only a small number of expert users. And with these type of methods, we would like to be able to bring it to non-experts. So this is a sample of a system that we have designed. In this case, we already have, we assume as input, a character that can be 3D printed, and now we would like to be able to animate this character as similar to virtual characters. So in order to handle this task, a user is going to specify a given bone for this character, and the user is going to draw a corresponding motion curve. Our system is going to bring a corresponding mechanism that's going to satisfy this motion. And we can repeat doing this for different types of joints, and in the end we can actually obtain mechanisms with very complex structures that can be directly 3D printed and assembled together. So how do we do this? Well, there's no free lunch here, and you have to start somewhere. We have to start, in our case, we start with a library of mechanisms. So there are a number of mechanisms that actually can produce a huge variety of motions. What's really interesting about it is that we make these mechanisms parametrized. So even if you take this very simple 5-bar linkage, you will see that it spans a very large space of different motion trajectories. If we are going to start changing the parameters here, you will see that the corresponding motions that this simple mechanism provides can be fairly varied. And again, this is a very, very simple structure. Okay, so we have the database of these parameterized components, and the next step in our case is going to be a sparse sampling of all of the parameters and pre-computing different parameterized motions. And then when the user performs the drawing of the curve, our system is going to bring the corresponding mechanism that has the closest matching motion trajectory to the desired one, and is going to do a small refinement using some continuous optimization. And this happens to work actually fairly well. There are a few bells and whistles that we also provide. So for example, if you would like to change different phase between the motions of different legs in this case, you can do this with a very simple interface and just changing the phase of the connecting of the two gears. We can also provide custom velocity profiles, and this is used using non-circular gears and specifying with user interface how the velocities should change as function of time. Once you specify the motions for all of these parts of the character, it's often very useful to drive this with only a single motor. So in this case, we also provide a relatively simple user interface that just allows you to specify how many different parts should go in between, and the system automatically connects these parts together. Using this system, we have designed a number of different mechanisms. This is just a sample of those. And we have fabricated actually most of them. I would like to show you some of the examples in detail. So this is a pushing man that many of you probably have seen. And if you would like to give it to a design of this to a casual user, it will be extremely hard. Using our system, this can be done within a few hours even for non-expert designer, including 3D printing and assembly. This example shows that we can also build mechanisms with internal driving. So in this case, it's just nothing more than specifying the constraints for the system where the mechanisms should lie. In general, the current system only allows you to specify planar motions, but it's fairly easy to combine motions in different planes to achieve motions in 3D. I would like to show you some limitations. So this is all limited to the kinematic design, and of course we are very interested to extending this to physics, such that this little character actually can really walk and not fall down. Okay, the last project I would like to present is really extending this to more and more complex things. So how can we do this? I mean, how can we make a leap from these little characters to something like a car? Well, of course, I would like to say there's no free lunch here, and our approach in this case is to use a data-driven design. So we are going to start with a database of fabricable and parameterized designs that are designed by expert designers. And we also are going to provide tools that are going to provide some mashup of these different designs, a composition tool that's going to fuse them together to produce more and interesting designs, potential designs that can satisfy some desired goals. So let's look at the database. I have been working with a group of talented mechanical and electrical engineers that built a sample database in this case. And immediately when you start building even something very simple, you will observe that you don't have, that these are really not computer graphics models. You have suddenly thousands of different parts, even for relatively small designs. So this is very different than traditional graphics models that we see. What's really interesting about our designs that all of them can be manufactured. So all of the components point directly to some online catalog that tells you how you can actually purchase this component and obtain this. So they point to real physical things. And our designs are also parameterized. So since we cannot really design many of those designs, we have to sort of expand the database. And in this case, similar to all these geared all of these linkages, we also make each of these designs completely parametric. And as you can see, these designs can have both continuous parameters and discrete parameters. So as I extend this part, the number of the connectors here change. Okay, let's talk about our modeling or composition tool. So it looks roughly like this. You can start very simply by taking one of the original designs, and you can the user can play with different parameters, changing where each of the components can be located. What's really even more interesting is the composition. How can we create composition of different parts from different objects that were originally designed? So in this case, we provide tools that allow you to snap the components and resize them automatically. We can handle articulated models. So for example, if we bring these doors to this cabinet, it knows automatically that it should resize. It looks for cabinets that are similar and sort of figures this out automatically using the data. If we bring this, for example, this drawer, it looks for the corresponding connecting mechanisms that should be copied from similar structures. This shows that if you try to put, for example, a wooden tabletop on the top of this table, the corresponding connectors are going to be very, very different. And again, the system allows you to use the data that's already stored to figure this out. We also provide some physics simulation here. This is extremely important. We really haven't done a lot, but we obviously think that this is something that needs to happen more and more. So in this case, it's just a simple way of evaluating whether a given design is stable or not. And of course, this provides an interactive feedback to the user. This shows an interactive modeling session, and I think this is something that a casual, non-expert user could potentially be able to do. So in this case, the user just brings and drags corresponding components from a database out. The system automatically resizes those, and finally, when the design is ready, everything can be ordered, and the whole design is completely manufacturable. What's really nice about this approach is that it's really all about data and extracting information from the data. So the same system that can be used for building, for example, furniture, can be pretty much used to build go-karts. And we have managed to build some go-karts and even to drive them in the building. It was winter, so we had to drive in the building.
MIT winners.
Yeah. Unfortunately. No breakdowns? No breakdowns. Okay, so this is a CS audience, I think mostly CS audience. I don't think I have to convince you that abstraction is really crucial if you would like to be able to scale the complexity of 3D printed or fabricated objects. So it's extremely important. And there's lots of interesting problems that encompass computer graphics, simulation, geometry, HCI, data-driven methods, machine learning, optimization. So lots of very interesting stuff that's very interdisciplinary, even within the computer science. Putting this talk in the bigger context, I really think that being able to have these output devices that are inexpensive, that are very powerful, it's going to really bring us closer to bridge the gap between virtual and real. And I really think this is very powerful, and I see a really greater role for computer science here. It's really going to hold as a glue to acts that keeps everything together. And as I said, we are going to see more and more interactions between computer science and other disciplines, disciplines like bioengineering, architecture, material science, or mechanical engineering. I would like to acknowledge my collaborators, students, and the funding agencies, and that I would like to conclude the talk with that. Thank you. Open for questions.
Seems to me the voxel is awfully small as a unit to be working with. Is there something equivalent to raster graphics for this space? Vector graphics.
Vector graphics. So I would like to say that yes, and I think it almost comes more from a different fabrication method. So what I have talked about is a very good abstraction for printers that 3D printers that print using rasters. There is a class of printers, such as FDM printers, for example, MakerBot style printers, that print using vectors, basically having a small filament that moves and prints as vectors. So I think there are very interesting questions about how can we build similar abstractions for vector-based 3D printers, and how can we have abstractions that mix both raster-based and vector-based 3D printers.
In addition to 3D printing, maybe analogy of vector graphics would be, you know, say if you're having a material such as wood and you cut out a particular piece, and I think you had some examples of this.
Yes.
I think there is a way to combine these two approaches.
Yes and no, and I want to say that you will probably need very different abstractions for manufacturing wooden patterns. For example, if you want to manufacture something out of wood, it's more of a process, because you are going to, for example, first cut the wood, then you are going to apply some coating layer and so on. So I think the underlying process might not be inherently local. It's going to be a fairly global system. So in my opinion, some of the low-level abstractions probably should change in this case.
Did you have to build your library of mechanisms yourself, or are there things available out there somewhere?
There are definitely things available, and I think this is going to be a very interesting area of future work or research. How can we reuse CAD designs? So I think this is a very, very interesting area for future work.
But you had to build your own library
Yes,
from
there are lots of difficulties with that reuse, in my opinion. We have how to make everything compatible. It's very difficult to make these designs compatible. If you would like to fuse designs that are made by two different peoples, it might be a problem. That's why before we did the project, we almost had a training for all of the mechanical engineers that were designing this, sort of to agree on some set of rules, at least at high level, how they should design. Yes.
Well, it's sort of equivalent to the idea of putting together a formal specification for the threads on screws, and the sizes of screws and the lengths of the shafts. And that sort of
Something like that, yes, but I think more at a high level, I would say.
It would be worthwhile to have a formal way define functionality, so that you don't just store a CAD model, you store a function of the model.
Yes.
Then you know you can adapt it for something else.
Absolutely.
Right now we don't have that.
Yes. That would be very nice. I agree.
Your talk is obviously on algorithms and representations and languages and issues and user interfaces and all of that. I'm having trouble relating that to any kind of a real-world type manufacturing machine. You seem to be printing plastic and metal and glass and wood and paint surfaces, and I'm not sure what machines exist currently that can be doing output in those kinds of materials simultaneously.
I think at the low level, right, you can build definitely components from all of these. You can definitely build components in all of these materials, right? I think what's really interesting about this is that for low-level tools, you probably need all of these interesting abstractions to make the fabrication processes scalable. At the high level, I think you can use these data-driven composition tools for a variety of different methods. So you can, use things that are 3D printed, things that are non-3D printed. So this is, I don't sort of see this as a big problem when you actually build things from components. And there's a large category of objects that actually are built from components.
But you're talking about like doing bulk materials that have multiple materials at a per voxel level with checkerboard.
At the low level, yes, of course, yes.
And the idea is that would all be printed at once, growing up from a layer?
Yeah.
Has any machine ever been able to do that with glass, for instance? What printers now exist that can do more than one material at a time simultaneously?
There are a number of industrial machines, both 3D systems and Stratasys have these machines. As I said, The problem with, I think, the main problem with these types of machines is that these are closed architectures, and it's very difficult for external people to experiment with these architectures. For example, if you would like to develop your own material, it's pretty much impossible. So that's why this prompts us to build research platforms like this, so we can experiment with the whole pipeline.
But it sure seems like the issue is material science and
Absolutely.
problems, not representations. Like being able
Both.
to fabricate wood, for instance, seems like a very difficult task.
Absolutely. So there are absolutely lots of interesting material science questions over there, and there are lots of people, the material science people who are working on this problem.
Glass lenses, and for lenses to be useful, they have to have, surface smoothness on the order of wavelengths.
Depends on the type of application. Yes, but you can potentially obtain this with special manufacturing processes, even within the context of additive manufacturing.
You can do that now. You can buy these things.
There are
hypothesizing that might be possible someday.
There are already, a number of companies that are working specifically on that.
One of the interesting applications that's thought to be successful is the creation or printing of organs.
Yes.
For medical purposes.
Yes.
How do you distinguish that from the making of rhinoceros dolls for your desk?
I think there are definitely lots of interesting questions over there. And depends what types. Over there are at least two different ways in which you can do tissue engineering. One of them is printing scaffolds. So whenever you're printing scaffolds, this is very similar to this, right? If you're printing cells directly, this is definitely much more challenging. Lots of interesting issues on the biology side, so, and people are really actively trying to figure this out. Lots of people working on this. I think on the simulation side, what's probably very interesting to look also at the time domain. Because whenever you're printing something that's live, you would like to see how is it going to change over the period of the time. So I think looking also, you would have to also look at the time aspect over there as well.
I saw an announcement of a device that used growing bacterial cellulose as the primary mechanism for building the scaffolding. Is that something which is moving into the mainstream, do you think?
There are definitely some startups working this technology. What's going to pan out of this? That's interesting. I wish them success.
I thought it was interesting that they would be trying it.
But they are definitely trying.
That's very, very curious.
Yes.
A cell is an incredibly complicated thing to actually print a cell. We're not going to do that anytime real soon, right?
No, right. So
We're going to maybe print a virus.
I think you're wrong.
People are growing cells and printing heterogeneous structures from the cells that have been grown already.
Oh, yeah, but you got to grow the cells. You can't print a cell.
Right. Yes. Yeah. Absolutely. Yes.
Right.
Yes.
I think we could probably do a nematode about that.
Even a cell of a nematode. Good luck.
You talked about this in terms of new manufacturing, which is effectively printing. How about old manufacturing? Wire EDM, mills. Can you drive the same sort of issues exist there, and does the same thing fit into the framework?
Some, yes, but I mean, you are talking about printing, designing electronics, and
Well, just
if
as
you
long as I've got all the cool tools, why can't I also?
yes,
run,
well, absolutely. I mean, I think there is a slight difference in terms of subtractive methods versus additive methods. I think the abstraction has to be somewhat different whenever you work with subtractive, because working with multi-layer structures over there is a little bit more.
There's things in the way and stuff.
So I think manufacturing process pose some specific limitations that I think your abstraction should handle.
But the subtractive processes, do they do they have beams that taper.
Yes.
But is there much more complexity in the sort of variation, like your metamaterial? I can imagine making that out of bulk steel by varying the number of pinholes I put per area.
Yes.
And make, but you can't, that's very complicated to think about unless you're taking the same approach of dithering and.
Yes, I think that there are definitely. I would say it's harder because I think there are more limitations coming from the fabrication process. A combination of additive and subtractive is even harder because you can also imagine growing something, then sort of shaving parts of it, growing more, and so on. So I think the algorithmic complexity of these processes is even more difficult. I don't think people in CS have even tried to attack any of these problems. But this is definitely something that we are capable of doing. Yes.
You're a tool builder. What tools do you use to build your tools? Like what programming languages, what kind of interactivity in terms of systems you're using?
We are trying, of course, to reuse a lot of the existing open source tools.
Are you using imperative languages or object-oriented languages?
No, we're using C++ mainly.
If you just make a block of plastic, how dense is it relative to the raw material? Has it got air pockets in it?
So printing air pockets is inherently hard because in order to print an air pocket within a material, you have to you have to introduce some support structures.
Wrong layer.
Yeah.
At the voxel layer,
Yes.
are there little air pockets between the blobs of plastic that you put down?
Depends on the manufacturing process. Typically, in the process that we use, we do not have any air pockets. In other types of, for example, in FDM-based process, you definitely have these air pockets that you can introduce. So this depends on the manufacturing process.
Are the voxels really solidly attached to each other?
Yes.
Or
In our case, yes. Yes. Absolutely.
So if I had a prototyping lab and I printed out a fantastic machine and I then wanted to put it into mass production, what is around that would help do that? I assume that mass production mechanisms today
Yes.
are quite different than printing mechanisms if I want high volumes.
Is it like injection molding, for
Injection
example?
molding is a good example, but vacuum forming even is,
Yes.
is
So
different than
yes. So I think the interesting part over there is you inherently limited. I would say with a something that's fairly uniform material, and I think it's so. This is and we are specifically trying to address the multi-material nature of 3D printing and having this very high spatial variation, being able to have materials with very high spatial variation. And I think having these capabilities, and people have shown that, of course, it gives lots of interesting materials with very unusual material properties that cannot be obtained using traditional methods.
I agree. Any more questions?
Not to harp on reality, I'm still having trouble relating this to something that might be built with multiple materials.
Yes.
You seem to answer a few questions saying basically some assembly would be required. You fabricate the parts and then put them together. But if you're talking about combining a dozen materials at the voxel level,
Yes.
that has to be done as a process.
Yes,
In an integrated
absolutely.
circuit, you don't glue the transistors together afterwards. So what, in your lab, what do you have running that can print with more than two materials at the same time in a single integrated structure?
This is Blue Box, you did it.
What can we
Do you actually have things working in your lab that can print multiple materials?
Of course.
What materials?
Well, basically, we are mostly working with polymers. We are mostly working with polymers, but polymers that exhibit different types of properties. Polymers that have different mechanical properties, optical properties, conductive properties. That's the extent.
I want to go back to where John was just a moment ago. You said, John, that semiconductors, you don't put pieces together to try to build a structure. I know of some semiconductors that are in fact done that way. And the question, I guess, that comes back to is, what's the scale here? How big's the voxel? How small can it be?
Well, depends on the technology. I think if you work with existing things and you would like to do things very, very fast, for example, HP had announcements some time ago, so that the inkjet-based technology, that's probably going to have the limits of around some very small, low microns, I would say. I think it's probably going to be very difficult to go sub-microns. It's probably going to be low tens of microns in terms of resolution. So this gives you roughly, hundreds of dots per inch. So, yeah, yeah.
So there's
By 2000 standards, it's awfully big it's awfully small by 1950 standards.
Well, I know, but this is we're now in the 21st century. And things are a lot bigger than they used to be, or smaller, depending upon your perspective. So, can you see the technology extended to dealing with really, really small things?
To nano, of course. I mean, there are obviously people working on nano-based printing technologies. Typically, they are much slower, so it takes a while to do something. But maybe they can be. This is not something that I personally work, but there are definitely lots of people working in that area.
Then we've seen some people who were talking about building printers for buildings.
Well, yes, of course, yes.
Where basically
Yes.
the element that is producing extruded material is a pressurized concrete.
Yes, absolutely.
And that strikes me as being sort of practical because it's fairly conceptually easy to deal with.
Yeah.
At all.
I haven't seen anything. I've seen some structures built this way. I don't think I've seen a real house
NASA is
built.
definitely doing work on that.
Excuse me?
Sulfur-based concrete.
Who,
On Mars. NASA.
Well, they should.
There was a conference here on campus.
Sure. Yes, absolutely. But I still haven't seen a real big 3D printed structure.
I saw some photographs.
Photographs of something that looks like a small house, but nothing like a real functional building.
Sports stadiums, I think, are being done.
Oh, okay.
Soon there are ways. Sports stadiums.
Who knows?
And I think this brings really an interesting point here is that most of printers, the sizes of the objects for most of the current 3D printers is limited to of course they have to be smaller than the size of the printer, right? I think what's really interesting is building 3D printers.
Wrong concept.
Yes, but what I'm saying.
Small printers and big things.
Exactly. Yes. Yeah. Exactly. But that moves you immediately in the realm of robotics. I would say you definitely, you are sort of, I think, solving lots of.
Trying to do for the shelf.
Yes, you are solving lots of robotics problems in this case, in my opinion.
So, are there facilities currently in place where people, organizations provide 3D printing facilities for building prototypes? If I wanted to go build a prototype of something, are there places I could go to do it? Because the printer is actually a small part of the market's need for things. You presumably you could use it for a short period of time.
Absolutely.
Don't use it for production because that's going to be too costly.
As I said, sometimes yes, sometimes no. Sometimes you are going to build a functional prototype. Sometimes, as for example, G is showing, you can use some of the parts to actually as real functional parts that you put in real products. So I think what's really interesting that I think being able to have access to all these technologies and being able to put a product that is composed maybe from a part that's 3D printed, part that's for example is CNC milled, putting them together. I think this is very interesting. I think there are lots of, efforts, even educational efforts at many campuses to establish the so-called maker spaces where students are learning how to use all of these technologies and how combine all of these technologies to build real functional products. And it's very exciting. I think most of the universities are trying to have efforts in this space.
Cool. Anybody else? You said you're going to present an equation relating the minimum feature size to the maximum volume to be done in an hour.
No more slides.
Because you can't do a football stadium
Yes.
one microdot at a time.
One of my colleagues is actually trying to do exactly this. He's in my mechanical engineering department, John Hart at MIT, and he's trying to actually, try to
Derive the law.
Yes, to actually derive.
It is, MIT, you're supposed to have, Maxwell's laws.
No, one theorem per talk.
And parallel processing, right? You're building this.
Yeah.
If you've got the vision, there's no reason you
Well-
can't use lots of little robots.
Well, sure. There's definitely some opportunities for parallelism.
The vision.
But per robot, there's still.
Well, you just do good cameras on the robots.
But per robot, there's a. And if HP's selling the ink, it's an awfully expensive.
Just as a rule of thumb, I know that about 5 years ago, no matter what machine you bought or anything, you had about 4,000 dots per unit length of the machine.
I see.
What's kind of the rule of thumb now?
I'm not sure if I understand. Could you
Well, you had about 4096 pixels or voxels that
Yes.
you could put across a device that was 3D printing something.
Yes.
Whether it was a 4-inch device or an 8-inch device or a
Yes.
2-foot device, no matter what it was about 4,000.
So again, if it uses, I think if it's typically it's limited by the technologies that are driven by printing industry. So people are reusing a lot of the same components that traditional 2D printing companies use. So that's why we are pretty much stuck in whatever 2D printers can do these days. I mean, the limitations I think are inherently similar, and sort of economies of scale I think are very, very similar.
Printers are incredibly fine scale. They
Yes.
put out picoliters and
Yes. Sure.
periods that are really
Sure.
small.
Yes.
But for 3D printing, you're putting out bigger
Yes.
resolutions, and the resolutions dots per inch or dots per
Yes.
meter.
Yes.
The question is what's the number of dots per unit length that's kind of state of the art today?
So I think there are definitely consumer-based printers and there are commercial printers. Commercial printers, in general, have much wider print heads, right? They can print with more nozzles. That they can actually output more. So I think no.
I don't know.
I think large scale.
I look at 72-inch Epsons,
Yeah.
and they have the same resolution that a desk plotter Epson has.
Yes, resolution. Yes.
The resolution is
Yes.
kind of the same. It's
The resolution just yes, but the width of the print head is larger. Yes.
resolution is so much per inch.
Right. Of course.
And what do you see the state of the art today as opposed to 5 years ago when I said it was 4096?
I don't think this is really changing that much because I don't think people need more. I mean,
What is the state of the art? How many dots per inch can you do in your lab?
like 600 dots per inch, pretty much. I mean, this is maybe people fake, maybe 1200 or something like this. So you can potentially do,
Just like everybody else.
Yes, please.
What do you expect to be the most important commercial applications of the commercial 3D printers, say in the next 5 years?
The most important commercial application I think we'll probably see being able to do functional parts very, very well, essentially better, and especially functional prototypes. So I think you will probably be able to design a prototype that sort of looks much closer to the original product. So I think this is going to be very interesting because it will allow people to iterate on designs very, very quickly.
My non-informed opinion is that when I look on Shapeways, that economically it'll be jewelry for women.
No, I think it's rocket engines.
Yes.
Like, but there are lots of things that would be very difficult to do, like a shaver, for example.
I know.
Yes. Yes. But I think this is going to be interesting how to extend the boundary of what can be done today and sort of be able to print a shaver actually.
Yeah.
So I think this is going to be really very interesting. And I think it's going to be happening. So basically, we'll be extending the range of things that we can do.
So what about intellectual property here?
Yes.
Copying parts is pretty easy.
Yes.
There are parts you can't make with a 3D printer, not because you can't be done, but because it's illegal.
Yes.
Parts for certain kinds of guns.
Cool.
The design files are available online, of course. We've seen the dilution of intellectual property rights for written materials sort of going away, although there's still some pushback. What happens here? This is presumably going to allow anybody to make one-offs of anything.
Yes, and I think there are lots of very interesting questions in this space, right? How can we incentivize designers to actually produce very interesting, high-quality models, right? This is real work, right? How can we do this? How do we have things that are open source? Do we have a Netflix model where basically you have access to a big repository and then you can download and print? I have a monthly subscription. Do you print, do we have...
It's easy, we just put a DRM module.
Oh, that's not that easy, right?
DCMA, the robot comes out and takes your stuff.
Yes. So I think lots of very
The printer makes a gun and shoots you.
And then it shoots itself.